Let's talk about neural shading deployment. We begin our transition story with application that we developed before, where we use Slang and Python for training a neural network to produce this Slang logo picture. We use SlangPy Python model for interface between Python, Slang, and graphics APIs. Now we would like to make a transition and replace Python implementation with C++. We keep the same Slang shader code. And of course, we will be using direct interface between C++ and graphics APIs. Let's take a look at our current Python implementation. We start by loading Slang source code, and for that, we use SlangPy model. First, we load Inference Slang source code from file, and then we create window interface with attached Vulkan graphics device. Next step is conversion of neural networks parameters. We convert them to cooperative-vector layout, and for that we use device cooperative-vector interface. Then we create device buffer for storing neural networks parameters and output texture. On the last step, we call inference function. Internally, SlangPy run inference compute shader, but from Python code it looks like we just call inference function from inference shader code. Now let's take a look at our C++ implementation. We start by loading compiled compute shader. For compilation, we use Slang C compiler, which is a separate application in Slang package. Next, we check cooperative-vector support for our graphics device. After that, we convert neural network parameters using graphics API interface. And then we create device buffers and texture. Last step, run inference. For that, we set up compute pipeline and then run compute shader. Step 1 is Slang code compilation. For that, we use Slang C compiler. And we need to set two additional flags: capability SPV cooperative-vector NV and capability SPV cooperative-vector training NV to enable using cooperative-vector extension in our Slang shader code. Slang C compiler produces shader binary files, DXL file for DX12 and SPIRV file for Vulkan. And it makes sense to use CMake similar tool to automate Slang code compilation. On C++ side, we just use graphics API to load binary shader code. Another possibility is use Slang API to compile Slang source code. We still need to set capability flags, but we can also define compile time parameters, set template parameters, and use reflection API to analyze Slang source code. Slang API produces shader binary code that can be directly used in graphics APIs. In step 2, we check for cooperative-vector extension support. For Vulkan, we initialize device with VK and V cooperative-vector extension, and then check that cooperative-vector feature structure has cooperative-vector and cooperative-vector training members both set to true. For DX12, first we call D3D12 enable experimental feature function to enable D3D12 experimental shader model and D3D12 cooperative-vector experiment features. Then we call check feature support to make sure that both D3D12 cooperative-vector tier 1.0 and tier 1.1 features are supported. Let's talk about matrix optimal layouts. You can see a piece of source code that implements linear part of the data transition between two neural layers. It takes cooperative-vector X as input, weights matrix, biases vector, and produces cooperative-vector output. It has parameter that defines matrix layout. It is important because tensor cores use custom matrix layouts. Components of matrices are shuffled between threads, and specific layout depends on the GPU and data types. So what do we need to create parameter buffer in optimal layout? First, we query shuffled matrix size from Vulkan or DX12, then upload row or column measure matrix to GPU, and convert layout on the GPU to inference optimal or training optimal layout. In Vulkan, we call VK convert cooperative-vector matrix in V for CPU conversion or size query, and VK CMD convert cooperative-vector matrix in V for GPU conversion. In DX12, we call get linear algebra matrix conversion destination info for size query and convert linear algebra matrix for GPU conversion. Then we create constant buffer and output texture. Let's take a look at Slang and Python inference code. First, on Python side, we create output texture as a SlangPy tensor and set it as an output for Slang inference function call. On Slang side, inference function takes pixel resolution and network parameters as input, and then call network evaluation function to calculate output RGB values. Network structure describes three-layer neural network, and every layer described by network parameter structure that includes weights matrix and biases vector. You can see that on Slang side, inference function returns float 3 of RGB values, but on the Python side, it's output texture. And from Python side, we call inference function with SlangPy call ID function, but it's just integer 2 on Slang side. That's because SlangPy creates a compute shader that calls Slang inference function for every pixel of output texture. So we need to create such compute shader manually and call it from C++. We start with compute shader function definition and use dispatch thread ID as an input pixel coordinates. Call inference function using pixel XY coordinates and put output RGB value into output texture using the same pixel XY coordinates. We use constant buffer to pass resolution parameter into compute shader and create network structure instance in the global namespace. It's important to correctly fill and bind all necessary buffers. After that, we add compute shader definition into our Slang source code, and now it's ready to be called from C++. On C++ side, we first initialize neural network parameters buffers, then set up constant buffer, bind output texture, and then dispatch compute shader using output texture size. And now conversion is done. As you can see, Python and C++ versions produce exactly the same output. You can find corresponding source code in Neural Shading SDK using GitHub link or QR code.